Hi and welcome to another video. Today we are looking into a Canadian hidden quantum champion in the space of superconducting quantum computing, which is called Anyon. If you don't want to miss out on that one, then stay tuned for today's video as we are diving into the hidden champions of Canada. And with that, let's go right into it. So here we are on the website of Anyon, Anyon or Anyon Systems, a Canadian leader in superconducting quantum computing. And here we already see some of their systems. We see the maple leaf down here, so made in Canada. It looks a little bit like the famous gold ounces that are coming from Canada. Let's quickly go through the website and see what we can learn here. So, on the road to commercial quantum advantage. Our hardware-efficient qubits will revolutionize the industry. This means fault-tolerant quantum computing at a fraction of size, cost, and time. The future of commercial viable quantum computing starts here. And then we see the cube with, of course, a Q at the very beginning. So the cube is an all-in-one superconducting quantum computer that integrates seamlessly into existing high-performance computing, so HPC centers. And that is, of course, important because if you want to scale this, you probably need to include it into existing hardware architectures or into existing supercomputing centers to have this kind of mixed compute between high performance computing and quantum computing. And of course, we've been talking about these approaches in previous videos already. Then we see Snowflurry here. Snowflurry is an open source software library for creating quantum circuits and running them on quantum computers and quantum simulators. So then we see here what it looks like. So it is looking very similar, I would say, to what we kind of know from Python. So you see here this function kind of approach where you put some arguments in there. There's a print function, but you also see some new stuff like this push exclamation mark type of setup here. I think you can probably also create objects. There's libraries in there. So let's say, on the one hand, very specific, domain specific, but then on the other hand, also probably something that is feeling familiar, right? So it says here gigahertz state. So this is initializing a gigahertz state. Here it says 3 qubit gigahertz, and then you have the Hadamard gate control and readout functionalities. You have the user token host and so on. So this is related to the machine. So probably this immediately deploys via cloud. Makes kind of sense. Then you have the QPU here. So that is being generated then using these arguments here. And then you do the shot count. So how often, I guess you want to repeat that, and you read out the results as well as the time that it takes, and you print the results. So I would say quite intuitive what it does here, right? Now quickly to the partners. So here it says selected partners that they're working with. And you see a lot of institutions here. So Economy, Innovation et Energie, Quebec. Then here we see Canada, Innovation, Science and Economic Development. Calcul, Quebec, there's Waterloo University in here, Montreal, investment in Quebec, McGill, so many different players around here. I guess a lot of them from the academic world. Now let's quickly check out a little bit about the technology as a first step. So the superconducting technology, right? So quantum computers are machines that harness the properties of quantum states, such as superposition, interference, and entanglement, to perform computations. In a quantum computer, the basic unit of memory is a quantum bit, or qubit, which can only be detected at extremely low energy levels and at temperature close to absolute zero. A quantum computer with enough qubits has a computational power inaccessible to a classical computer, which is referred to as quantum advantage. Superconducting qubits are one of the most promising candidates for developing commercial quantum computers. Indeed, superconducting qubits can be fabricated using standard microfabrication techniques. Moreover, they operate in the few gigahertz bandwidth such that conventional microwave electronic technologies can be used to control qubits and read out the quantum states. The operation of a universal quantum computer is based on quantum gates that, just like the logical gates of a classical computer, perform basic operations. By programming these operations in a sequence, it is possible to implement any arbitrary complex algorithm. And then here are the main components. So you see the quantum processors, cryogenic systems, control electronics, and the software stack. And if I understand correctly, they own every single one of those. So let's start maybe with the quantum processors. So they are, of course, the circuits. They are the superconductors that host the structures that then act as a qubit. In order for them to work, you need to cool them down. That's why you need a cryogenic system, usually into kind of millikelvin range of temperature. Kelvin is, let's say, the physics way of expressing temperature, where 0 refers to the absolute zero. And then, 273 degrees Celsius, minus 273 degrees Celsius means 0 Kelvin. So the point at which water has its phase transition from ice to liquid is 273 Kelvin or 0 Celsius, right? At least at ambient pressure. Then you have the control electronics. Here they talk about ultra-fast FPGA-based electronics. There are companies also making those. We've talked about them previously in the Hidden Quantum Champions playlist. And then finally, there's the software stack, the SDK. Is based on Julia programming. That is, I think, a Python derivative for, let's say, high performance / numerical type of computation. So on a Julia based on a Julia programming language, and allows users to conveniently interface with the quantum computer to run an algorithm by defining a quantum circuit. And that's about what we can learn here for the technology. Let's quickly check out the products that they have already. So we have seen the Cube before. So the Cube is an all-in-one superconducting quantum computer that integrates seamlessly into HPC centers. The system's cryogenic and electronic system are packaged in a standalone unit. A modular design facilitates shipping, assembly, testing, and servicing. The Cube comes with a user-friendly human-machine interface and requires minimal maintenance tasks to our closed-cycle cryogenic system. The system was designed to be scalable such that it can be upgraded with quantum chips with increasing numbers of qubits. So that's kind of selling also a bit on the roadmap, right? The more qubits you have, the more qubits you have, the more powerful stuff you can do with it, obviously. Possibly today, and I haven't seen any number yet. Not sure if there's any number here on the website, but probably today there are not super many qubits on these chips, and of course this will scale after a while. That means you also need to have a little bit more of control electronics and so on. But as far as I understand, this is built in a way that you can later on scale these things up. And if I look at the size of this cryostat, I think it looks like this is a quite powerful one, so you can probably easily kind of strip more of these radio frequency lines down to the chip stage, or just put a bigger chip if you already have those down there. The minimal maintenance probably refers to things like refilling the cold trap with liquid nitrogen, but I'm not sure about that because it's not stated anywhere here. And then, of course, there's the Snowflurry software kit available as well. Let's quickly also hop into the news session. I'm recording this beginning of 2026. We see here September 2025, Anyon Systems becomes anchor partner in world-leading industrial quantum manufacturing facility. So Anyon Systems, Inc., or Anyon, a quantum computing company based in Montreal, Canada, is pleased to announce the collaboration with the C2MI, which will establish Quebec and Canada as a global hub for superconducting chip production and opens new opportunities in the quantum economy. So September 2025, this is January 2026. So I guess also looking at this 2024, not too much happening on the news side, but I guess still very much alive as a company. Let's quickly also check out the teams. There are different teams within the company, as it seems. So there's the quantum, which I guess is making the quantum processors, cryogenics, which is building the cryogenic systems, electronics, which is making these FPGAs, and also PCBs, as it seems, so including PCBs and FPGAs. The PCBs, printed circuit boards, are the boards that include all of the components that you need to build the electronic circuits for measurements, and then also the software team. Now the quantum team is designing the quantum chips, so probably designing as in, here. The quantum team's responsibilities to calibrate, characterize, and optimize the performance of the quantum processors and to design the chips. However, they also need to be fabricated in a clean room, right? And that's the nanofabrication team. So nanofabrication team uses latest micro and nanofabrication techniques to fabricate the quantum processors, using the clean room, of course. And then finally, there's also the manufacturing team. Manufacturing team is responsible for machining and assembling the parts that make up the quantum computer. Okay. I think there's nothing else to mention here. It says they have 2 offices in Montreal and Waterloo, both in Canada. And I guess, let me check. So that's, I think, everything for now that I wanted to share with you about this company. So I hope you liked it. I hope you found it insightful. If there are any open questions on that, of course, as always, please put them down in the comments below. If you stayed all the way till the end of this video, probably you will be interested in the next video as well. So make sure to subscribe to this channel. And with that, as always, stay hydrated and see you in the next one. Bye-bye.